You've probably heard that the distance from the Earth to the Moon is 384,000 kilometers. How do we know? Hi, I'm Dan Roy with my wife Rebecca here. We like to show the sky to anybody who wants to watch. You can certainly measure the distance to the Moon with a high-tech equivalent of a measuring tape. Here is a retroreflector. That's a cube, and the inside surfaces are perfectly reflecting. So if you shoot a beam of light here, it will be reflected with an angle here equal to that angle there, reflected again with those two angles being equal again. And by using Euclid, you can prove that those two beams are parallel. So whatever you throw at it, it will come back at you with the same angle. Very convenient. And those retroreflectors have been installed on the Moon by our astronauts, and they allow us to measure the distance by measuring the time it takes on the round trip. And it also measured that the Moon is moving away from us at 3.78 centimeters per year, which is the speed at which our fingers are growing, the speed at which the continents are moving. Now this business of sending some energy, getting it back, measuring the time, is not new. We've done that with radar since World War II. And so we've done that in space as well with the mother of all radar, the 300-meter dish of Arecibo here on the island of Puerto Rico. But the problem with radar is that when you send P0 energy in space, what you get is P0 divided by the power 4 of the distance to the target. That's not much, but it's enough to image the North Pole of Mercury and produce this absolutely beautiful image of the surface of Venus from 50 million kilometers away. Quite impressive, but in spite of progress in microelectronics and cryoelectronics and signal processing, this particular method of ranging is valid to about 3 astronomical units. Good, excellent, but not enough to measure the distance to the stars. For that, we have to use parallax. So here is the principle. Bear with me here. Extend your arm, and at arm's length, flip the little finger up. I said the little finger guy, okay? Be polite. Now, when you do that, and you close one eye and then the other eye, you will see that your finger seems to move against a target on the wall. So put some kind of measuring device on the wall, do that, and measure the distance that you think your finger has moved. It is very easy to see this relationship here, and if you apply with the numbers I give you, you will be able to determine the distance based on the variation in angles, actually, between what your two eyes are seeing when you close them after the other. That's the principle of parallax. Now you can do quite a bit of angle measurement with your hands, okay? From 1 degree, which is the little finger extended at arm's length, to 25 here. And let's see that someone asks you, hey, I cannot find Polaris. You say, okay, can you see the Big Dipper? Oh yeah, sure, I can see Big Dipper. All right, can you see Dubhe? Huh? Okay, so that's the star at the end of the ball here, okay? We call it Dubhe. Now, if you can see this star, move 3 degrees to the right and 25 degrees up, and you will find Polaris. So that can be useful. It can be useful during the daytime as well. Let's assume you want to know the height of this tree here. So you put your tape at the bottom of the tree, and you keep moving back while keeping your hand extended in a 25-degree position here. And when you see that your thumb is at the bottom of the tree and your little finger is at the top, then you measure the distance. Let's assume that you find it was 19 meters or something. Then you can use trigonometry. You know that in a rectangle, a triangle like this, if you divide the opposite side by the adjacent side, you get what is called a tangent. Okay? Knowing that, and knowing that the 25-degree angle has a tangent of 0.466, you can easily compute with a 19-meter distance that your tree is about 9 meters high. Okay? Now we owe all that to Hipparchus of Nicaea. He was born in 190 BCE, and he was probably the best astronomer we ever had. He was a geographer, a mathematician. He invented trigonometry, for heaven's sake. He invented the trigonometry concepts of sine and cosine and tangent, and he was able to build his own trigonometric table. He invented the astrolabe and its 3D equivalent, the armillary sphere. He also had data from the Babylonians and people who were born and died before him, such as Aristarchus of Samos here, who was born in 310 BCE, and who, by the way, is credited with the invention of the heliocentric model. He discovered the precession of the equinoxes. Wow, that's pretty impressive. Probably thanks to the Babylonian observations. But as you know, the axis of the Earth is not fixed in space. It wobbles like a top, and it basically moves like a cone with a period of 25,772 years. So within 25,000 years, Polaris will be back where it is now. Okay. Now the famous book 7 from Ptolemy, the Almagest, who lists the star data that was used in the Middle Ages, is very probably based on Hipparchus' observation. And for good measure, during partial eclipse and total eclipse, he was able to determine the distance from the Earth to the Moon, and therefore from the Earth to the Sun, since we have a good fortune of having the same kind of angle. The Sun, like the Moon, subtend an angle of half a degree. Okay, now the distance we deal with in astronomy are much smaller than what you can do with your hand extended at arm's length. Okay, where 1 minute of arc, for instance, is one soccer ball seen from 8 soccer fields away. 1 second of arc is when the ball is 50 kilometers away. And that is where Jupiter sustained a 50 arc-second angle when closest to the Earth, which it is now, in July of 2020, by the way. The Hubble Space Telescope angular resolution is 50 milli-arc-second. And with big telescopes, we can do a little bit better than that with adaptive optics. But along the short of it, okay, this particular method, the parallax method, is good for about 100 parsec, because you can do better than 10 milli-arc-second of resolution. So that gives you enough distance capacity to go all the way to 320 light years. Okay, and that is good enough for about several hundred stars, and that's good enough for the entire Big Dipper, by the way. Now, let's have a look at what the parallax method looks like in practice. To do that, you have to imagine that you have eyeballs separated by 300 million kilometers, because the semi-major axis of the Earth is 150 million kilometers. So that's pretty big distance. Then you put yourself, okay, that's the key idea here. You put yourself at a distance from the Earth, from which half the Earth orbit, this distance here, would sustain 1 second of arc. So you go to a distance here, you measure this angle here, that's 1 second. The distance you have here is called 1 parsec, 1 per second of arc. Now, you measure how much the finger have moved between February and August, and you measure that in angle. And when you've done that, then the distance that you have between the Sun and this particular object is 1 second of arc divided by the angle you measured. For instance, if what you measure is half an arc second, then this thing is twice as far as 1 parsec or 2 parsec. And we have an equivalent, by the way, between parsec and light years. We're going to see that in a moment. So for instance, Sirius is about 0.378 arc-second, as measured against the background of distant star. That gives you a distance of 2.64 parsec. It turns out that a parsec is about 3.26 light years. Therefore, the distance between the Earth and Sirius, the Sirius and the Sun, is about 8.6 light year. And again, that's pretty good for for about the hundreds of stars that are close enough so that we can do that. And certainly all the stars of the Big Dipper are in that case, including Polaris, by the way, which happens to be at 320 light years away, at the limit of the resolution of the method, but we can still do it. Now, to go a little bit further, we have modern technology, and back in 2013, the European Space Agencies launched the Global Astrometric Interferometer for Astrophysics. Okay, it surveys 1 billion stars to the resolution of 100 microarcseconds. So it can measure distances up to 10 kiloparsecs, which is 36,000 light years. Now we start to talk about serious measurements, and this mission will be going on for another year or so. Now, in the part 2 of this talk, I will cover some of the more advanced methods, the Cepheids, the HR diagram, Type 1a supernova, Doppler shift. So, see you next time, and thanks for watching.